Hello and welcome back to this channel once again. Now, in the previous lesson, we defined the Laplace transform as an integral operator that maps a function of time into a function of the S domain, and we solved a couple of examples. Now, in this lesson, we are going to do the reverse process. What we are going to do is to consider the problems of finding f of t, which is the original function, the function of time, when the Laplace transform f of s is given. So we want to find this time f of t when f of s is given. So in other words, we say that we want to seek an inverse mapping of the given Laplace transform. So given a function f of s, if there exists a function f of t that is continuous on the interval close bracket 0, infinity open bracket, and satisfies the Laplace transform of f of t equals f of s, then what this primarily means is that f of t here is said to be the inverse Laplace transform of f of s, and employ the notation f of t equals the inverse Laplace transform of f of s. Now, what do we mean by this? This is what we are saying. If f of t, okay, is a function of time. So let's say if f of t is a function of time, and then we say that f of s is said to be the Laplace transform of f of t, then if we want to find the original function back, that is f of t, then we can say that f of t is nothing but the inverse Laplace transform of f of s. That is basically what we mean. So if f of t is a function and then f of s is said to be the Laplace transform of f of t, then we can find the original function f of t, and that is given by the inverse Laplace transform of f of s. Now, one thing you need to take notice of is the fact that finding f of s when f of t is given is not really a big deal. However, finding f of t when f of s is given is really stressful. Now, the reason why it is stressful is this time you want to do the reverse process. In as much as the reverse process is going to be really stressful, what is going to be of great help to us is the Laplace transform table. Now, since the Laplace transform table is not going to be provided to us in an examination, the only advice I'm going to give you is to try to know or to memorize the transform of some basic functions of time. Now, if you're able to do that, then it becomes really easier in doing the reverse process. So now let's move on to the Laplace transforms table. So this is the Laplace transforms table. We have f of t to be the original function, the function of time. So this is the function of time. This is also the function of time. And then we have this column and that column to be the Laplace transforms of each of the functions. So this is the function f of s, and that is also the function f of s. So the whole column contains, the Laplace transforms of the corresponding functions, and then same applies to this particular column. So assuming that you are given the Laplace transform of a function in the form 1 over s minus a. Now, if you know that a function of the form e to the power at is likely to produce the Laplace transform of such an expression, then it becomes really easy when you are given this Laplace transform and you want to find the original function. So for instance, assuming you are given the Laplace transform of the form or having the expression 1 over s minus 2. Now, since you know that the Laplace transform of the form 1 over s minus a is being produced by a function of the form e to the power at, then it becomes really easy in finding the original function. Now, if you want to compare these two functions, you have this, that is the function of time, e to the power at, and this is the function in the s domain, 1 over s minus a. So you compare a and then a here, and then you realize that the value here is basically the negation of the value you are going to have as exponent here. Therefore, since we have negative 2, then it means on top here you are going to have a positive 2. So this is said to be the function e to the power 2t. Therefore, the Laplace transform of this function is what we have here, that is 1 over s minus 2. And then the inverse Laplace transform of this function is the function e to the power 2t. So the Laplace transform of e to the power 2t is equal to 1 over s minus 2, and then the inverse Laplace transform of the function 1 over s minus 2 is equal to e to the power 2t. So as said earlier, it is very important to know the transforms or the Laplace transforms of some basic functions of time. Now with that, it becomes really easy in finding the original function back when f of s is given. So sometimes in practice, the Laplace transform given may correspond exactly to any of the entries in the third column or the sixth column. So like the example we just looked at, you realize that this fraction corresponded exactly or matched at least one of the transforms in here. Now with that, you realize that it becomes very easy to find the original function. Now in cases where the transform given does not match or does not correspond to any of the entries in here, then we need to manipulate the Laplace transform in order to obtain the original function. So in doing this, in manipulating the transform, we are going to rely on the linearity property of the inverse Laplace transform, and that is obtained from the linearity property of the Laplace transform. So considering the linearity of the inverse Laplace transform, given that the inverse Laplace transform of f1 of s and the inverse Laplace transform of f2 of s exist, and c1 and c2 are said to be constants, then the inverse Laplace transform of c1 f1 of s plus c2 f2 of s is equal to, basically we can split into two inverse Laplace transforms, so that we have the inverse Laplace transform of c1 f1 of s plus inverse Laplace transform of c2 f2 of s. Now because c1 and c2 are constants, we basically pull out the constants, so that we have c1 times the inverse Laplace transform of f1 of s plus c2 times the inverse Laplace transform of f2 of s. Now this is made possible due to the linearity of the inverse Laplace transform. So in the next section, what we are going to do is to consider problems of finding f of t, that is the original function of time, when the Laplace transform f of s is given. So now let's take our very first example. So in this example, we are going to determine the inverse Laplace transforms of the following functions for a, b, and c. So let's try these together. So for a, we want to find the inverse Laplace transform of the function 2 divided by s cubed. Now at this point, we are privileged to have the Laplace transforms table, and so we can easily refer. Now as I said earlier on, because it is not going to be provided to us in an examination, it is very important that we know the transforms of some basic functions of time. Okay, so that is going to help us. Now since we are privileged to have the Laplace transform table with us, let's go back to the table to refer. So we want to find the inverse Laplace transform of 2 over s cubed. So we should be looking out for the transform which has its denominator s to the power a value which is more than 1. So that is what we should be looking out for. So now we come to the Laplace transforms table, and then we have the first Laplace transform to be 1 over s, which corresponds to ft equals 1. Now here we have s to the power 1, so obviously this is not what we are looking at. We move on to the Laplace transform that corresponds to e to the power at, and then here we have 1 over s minus a. Definitely that's not what we are looking out for. We want to find a denominator which has s to the power more than 1. So we move on to the next one. Now here we have the denominator to be s to the power n plus 1. Now this suggests that we have the power to be more than 1. It is something plus 1. Yes. And then we also have a clue that this value should be equal to this value, that is ignoring the factorial. So it means that we can simply massage this function. Now if we are able to represent this as the inverse Laplace transform of 2 divided by s to the power 2 plus 1, then it looks like we are getting there. Now notice that these two values are supposed to be the same, neglecting the factorial. 2 factorial is equal to 2 times 1, and that is equal to 2. So we can simply represent 2 at the numerator as 2 factorial. Now the moment you are able to do this, then it means that this Laplace transform corresponds to the function t to the power n. Now in this case we have n to be 2. Therefore we say that the inverse Laplace transform of this function is equal to t to the power 2. That is the inverse Laplace transform of the given function. Now let's move on to the second one. So here we want to find the inverse Laplace transform of the function 3 over s squared plus 9. Also for this, we should be looking out for the denominator which has s squared plus a squared. So we come to the Laplace transforms table. For sin at, we have the denominator to be s squared plus a squared. For cos at, we also have s squared plus a squared. Now let's look through to see if we have s squared plus a squared. So this we have s squared plus a squared, but we have the square of it, so we are not going to focus on that. So apparently we are going to focus on sin at and then cos at. It could be one of these two. Now again, for sin at, we have a on top at the numerator, and then we have a squared also at the denominator. Now it gives an indication that the value here should be the square of this value. Okay, the value here should be the square of this value. Now we come back to the question, and then we have a 3 here, and then we have 9 here. Now we can simply represent 9 as 3 squared. So we can have the inverse Laplace transform of the function 3 divided by s squared plus 3 squared. Now the moment we have this expression, then what this primarily means is that this corresponds to the transform for sin at. It corresponds to the transform for sin at. Therefore we have a to be equal to 3. So we have a here to be equal to 3. Therefore the inverse Laplace transform of this function is equal to sin 3t. Sin 3t. Now to the last one, we have the inverse Laplace transform of the function s minus 1 over s squared minus 2s plus 5. So notice that we have an s minus 1 at the numerator. So we come to the Laplace transforms table. We are looking out for s minus a on top. S minus a on top. So we can have the function e to the power at cos bt, or we can as well have the function e to the power at cos bt. So any of these two forms could possibly be what we are looking out for. Now the moment we have an s minus a on top, then that should be equal to what we have here, and then we are going to square it. So for this we have an s minus 1 at the numerator. It means that we should have s minus 1 all square plus something else. So we can have s minus 1 all square plus b square. So let's consider number 9, which is e to the power at cos bt. Now if it's not that, then probably it is for this, that is e to the power at cos bt. So first let's check out for e to the power at cos bt. If we don't get the right answer, then we can possibly verify for e to the power at cos bt. So we can express this inverse Laplace transform as the inverse Laplace transform of the function s minus 1 divided by, we should have an s minus 1 here, and then the square of it plus b square. So what we are going to do is to find the value, probably b square or b. So we have the numerator to be the same. We are going to compare the denominator. So we are going to equate the denominator. So on the left hand side we have s squared minus 2s plus 5, and that is equal to, on the right hand side we have s minus 1 all square plus b square. We want to find the value of b square or b. So on the right hand side we have s minus 1 all square, which means that we have s minus 1 times s minus 1. So we multiply s by s, we have s squared. We multiply s by negative 1, that is negative s, and then negative 1 times s, which is also negative s. So negative s minus s is negative 2s. Negative 1 times 1 is 1, and then plus b square. So on the left hand side we have s squared minus 2s plus 5. Now because we have s squared on both sides, negative 2s on both sides, we are basically going to compare the constants. So we compare the constants. We have 5 equals 1 plus b square. So if you want to find the value of b, we basically transpose 1 to the left hand side. That becomes a 4 equals b square. Then we have b to be equal to plus or minus 2. So we can basically input plus 2 here or minus 2 here. Now we should realize that we are looking out for the function having the form e to the power at cos bt. So let's just put that somewhere here. So we are looking out for, let's say, the function e to the power at cos bt. Now this b is the value we have here. Now notice that cosine is an even function. So whether you have positive 2 or negative 2, because it's an even function, you are going to have the same results. So let's possibly take the positive value. Okay, so we can further express this as the inverse Laplace transform of s minus 1 over s minus 1 all square plus 2 square. Then this becomes, we have e to the power at. Now don't forget that a is equal to 1. So we have e to the power 1 times t times cosine of bt, and then b is 2. So 2t. Therefore we have the inverse Laplace transform of this function as e to the power t cos 2t. Now let's move on as we solve the second example. Now for the second example, we are going to find the inverse Laplace transform of this function. So we have the inverse Laplace transform of the function 5 over s minus 6 minus 6s over s squared plus 9 plus 3 divided by 2s squared plus 8s plus 10. Now using the linearity property of the inverse Laplace transform, we can split this whole function into 3 separate functions. So we can have the inverse Laplace transform of 5 over s minus 6 minus the inverse Laplace transform of 6s over s squared plus 9 plus the inverse Laplace transform of 3 divided by 2s squared plus 8s plus 10. Next, because we have constants, we can pull out the constants and then we try to further simplify the function. So we can pull out 5. So we have 5 times the inverse Laplace transform of 1 over s minus 6 minus, we pull out 6 times the inverse Laplace transform of s over s squared plus 9, and then here we have a 3 here, and then notice that we have the coefficient of s squared to be 2. Now in all the transforms, you realize that the coefficients of s squared should be 1, and so we can factor out 2, so 2 comes out, and then we have times the inverse Laplace transform of 1 over, so that we have the coefficient of s squared to be 1, so s squared plus 4s plus 5. Now we are going to find the inverse Laplace transforms of these 3 functions. So first of all, for 1 over s minus 6, we can look out for 1 over s minus a. So we come back to the Laplace transforms table. For 1 over s minus a, we have this time a to be 6. We have a to be 6. So it means that we are going to have the function of the form e to the power at, and then if a is 6, then we have e to the power 6t. So we are going to have 5 times e to the power 6t minus 6, the inverse Laplace transform of s over s squared plus 9. So we are going to look out for s over s squared plus a squared. Okay, so that corresponds to cos 80. Now we have a squared to be 9, so we can represent 9 as 3 squared. Now if we are able to represent 9 as 3 squared, then it probably means that we have cos 3t. We are going to have cos 3t. If this is 9 and then we represent that as 3 squared, then it means we have a to be 3. So that's going to be cos 3t. So we have negative 6 times cos 3t, and then plus 3 over 2, and then the inverse Laplace transform of this function. Now here we have 1 over s squared plus 4s plus 5. So we come back to the Laplace transforms table, and then we look out for the transform of e to the power at sine bt. So here we have b over s minus a all squared plus b squared. So since we have this to be 1, we have the numerator to be 1, then we should represent the denominator as s minus a all squared plus b squared. So we are going to have 3 over 2 times the inverse Laplace transform of this, and that's going to be the inverse Laplace transform of, we are going to represent this as 1 over s minus a all squared plus 1 squared. Now since we don't know the value of a, we are going to equate these two denominators and we try to find the value of a, and then we insert that back into the function. So we equate the denominators. On the left hand side we have s squared plus 4s plus 5, and that is equal to s minus a all squared plus 1 squared, which is simply 1. So on the left hand side we have s squared plus 4s plus 5, that is equal to s times s is s squared, s times negative a as, negative a times s is also negative as, so that becomes negative 2as plus negative a times negative a, that is a squared plus 1. So first of all, we are going to compare coefficient of s. We compare coefficient of s. Now coefficient of s on the left hand side is 4. Coefficient of s on the right hand side is negative 2a. So we have 4 equals negative 2a. We divide through by negative 2 by negative 2, and then we have a to be equal to negative 2. So this is the value of a. Now we are going to put the value of a into this transform. So we are going to have 5 times e to the power 6t minus 6 times cos 3t plus 3 over 2 times the inverse Laplace transform of 1 over s minus, so minus minus becomes plus, so s plus 2 all square plus 1 square. So this becomes 5e to the power 6t minus 6 cos 3t plus 3 over 2 times, now we have this value to be b. Okay, we have this value to be b, and then we have a here also to be negative 2. We have a also to be negative 2. So that's going to correspond to e to the power at sine bt. So that's going to be e to the power, a is negative 2, so negative 2t, and then sine bt. b is 1, so sine t. 1 times t is still t. So we have e to the power negative 2t sine t. So e to the power negative 2t sine t. So finally, we have the inverse Laplace transform to be 5 e to the power 6t minus 6 cos 3t plus 3 over 2 times e to the power negative 2t sine t. Now let's move on to example 3. So sometimes you can be faced with rational functions which are given of the form, so rational functions which are given of the form p of s divided by q of s, where both p of s and then q of s are polynomials, and the degree of p of s is said to be less than that of q of s, where q of s is not equal to 0. Now in such cases, we can break down the complex rational function into the sum of simple rational functions so that we can move on to find the inverse Laplace transform. So for this rational function given, we have f of s. We have f of s to be s plus 11 divided by s minus 1, s plus 3. Now the denominator has linear factors, and so we can decompose this using the method of partial fractions, so that we have a divided by s minus 1 plus b divided by s plus 3. So let's try to find the values of a and b. So we have the LCM to be s minus 1, s plus 3, and then s minus 1, s plus 3 divided by s minus 1. This will cancel that, and then we are left with s plus 3. So we have a times s plus 3. Here also, this divided by that, this cancels that, we are left with s minus 1. So we have b times s minus 1, and then on the left hand side we have s plus 11 divided by s minus 1, s plus 3. So you realize that the denominators are the same, so let's focus on the numerators. So we are going to equate the numerators, and then we have s plus 11 equals a times s plus 3 plus b times s minus 1. Now we are going to put let's say s equals -3. In that case, a goes to 0 and we can find the value of b. So on the left hand side we have -3 plus 11, and that is equal to a goes to 0 if we plug in -3, so in place of s. And so for b we have b times -3 minus 1, and this becomes -4b. So we have -3 plus 11, that is 8, equals -4b. Now we divide through by -4 by -4, and then we have b to be equal to -2. So this is the value of b. Again, we are going to put s equals 1 so that b also goes to 0. On the left hand side we have 1 plus 11 equals a times 1 plus 3. This is 4, so 4 times a is 4a. So we have 12 equals 4a. We divide through by 4, and then we have a to be equal to 3. Therefore we can further represent, or we can represent the Laplace transform given as 3 over s minus 1 minus 2 over s plus 3. So from this it becomes very easy in finding the inverse Laplace transform. So now we are going to have the inverse Laplace transform of this function. So that becomes 3 over s minus 1 minus 2 over s plus 3. Now using the linearity property of the inverse Laplace transform, this is equal to, we factor out 3, we have times the inverse Laplace transform of 1 over s minus 1 minus, we factor out 2 times the inverse Laplace transform of 1 over s plus 3. Now 1 over s minus a corresponds to the function of time e to the power at. Therefore here we are going to have 3 times e to the power, a is 1, so e to the power 1 times t, which is e to the power t, minus 2 times e to the power, this is plus 3, so it becomes -3, so minus 3t. Therefore we have the inverse Laplace transform to be 3 e to the power t minus 2 e to the power -3t. So that's it for today's video. Thanks for watching, and see you in my next video. Bye bye.